For the last problem, 7.72, we have again a common source amplifier, right? So it means that the source here is grounded, here's the gate, here's the drain. And given a transconductance of 2 milliampere per volt, we know that we have an overall voltage gain. So considering this one here, we have an overall voltage gain of minus 10 volts per volt. So that's the characteristic of this circuit here, with the source grounded. Okay. Now, suppose we insert a resistor at the source, and what should be the value of this resistance for an overall voltage gain of minus 5 volt per volt? Okay, so if we insert this resistance here at the source LED, we basically change the overall voltage gain, and we want to get this minus 5 volt per volt. So what should be the value of the source resistance? Okay, so first let's analyze this circuit here. So we need this common source amplifier to get a relationship between the drain resistance and the transconductance. Okay, so if we know that the voltage gain, the overall voltage gain, GV, is equals to V out over this signal. Okay, so this one here over this one here. Okay, that's what we know. Now we know that we can write the V out 1 as, again, the polarity here assigned for V naught is plus minus, and this current here at the drain that I call ID1, it's flowing in the opposite direction. So we have to take minus that GM VGS times RD. Okay, so if we take this ratio V01 divided by VGS, and we realize actually that VGS here is equals to the input source signal, because there's no current, so this current here is 0 amperes. We get that this signal is equals to minus GM over RD. And this is important because we know this relationship here. That's the first overall voltage gain that we have, that minus 10 volt per volt. So this minus 10 is equals to minus GM RD. Okay, and this RD GM is actually 10 volts per volt. Okay, so that's RD over GM. Now suppose we include a source resistor in this circuit, right? So now we have an ID2 flowing here, and this VGS is no longer equals to V signal because there's no 0 here anymore. Now we have a voltage Vs that's equal to Rs times ID2. So our VGS, okay, I'll call Vs, small vs, is equals to V signal, which is this potential at the gate, minus the source resistance times, I'll call ID2 because we are analyzing the amplifier, so it should be small i's here. Okay, and we know that this current ID2, this ID2 is equals to Gm times VGS, right? It's forced by this current source. And this VGS is equals to that. So ID2 is equals to Gm. And this Gm is the 2 milliampere per volt that we have times this signal minus RS ID2. So if we isolate ID2 in this equation, we know that ID2 is equals to Gm this signal divided by 1 plus Gm source resistance. Okay, so that's the equation for ID2. And we can still have an equation for V02, for this one here, right? Again, it's just ID2 times RD, negative of that, because the current is flowing in the opposite direction as the polarity assigned for V02. So in this case, V02 is equals to minus RD times ID2. And ID2 we know here. So V02 is equals to minus RD times Gm, this signal, divided by 1 plus GMR source. Now if we isolate V02 over this signal, that is actually our new voltage, overall voltage gain. That's equals to minus RDGM divided by 1 plus GM RS. Now if you remember, this term here is actually the magnitude of the previous overall voltage gain that we had. So this new overall voltage gain, we want it to be minus 5 volt per volt minus that 10 volt per volt divided by 1 plus Gm, we know it's 2 milliampere per volt times the source resistance. So it's just a matter of isolating Rs in this equation here. So Rs is equals to 10 minus 5 divided by those 2.22 milliamperes per volt times 5 volt per volt. This one here is also volt per volt. This one is also volt per volt. And this gives us an Rs that is equals to 500 ohms. So in summary, if we go to this circuit here, this amplifying circuit here, that has an overall voltage gain of minus 10, and we change this circuit by inserting a source resistance here that's equals to 500 ohms. This gain, this overall voltage gain here of 10 minus volts per volt becomes this new overall voltage gain of minus 5 volt per volt.